Does anyone feel strongly about wanting some more time before I wanted to get this part of the lecture done before lunch. It's almost 11 o'clock because I wanted to be able to spend the afternoon doing other lab work as well. I realize that this is very fast and glossing over, and some of you are still probably at the point of being completely lost. I hope not, and I don't want you to leave today being completely lost, because I'd like you to at least be a little bit found, in that you can have these ideas of this is some spatial data. I can link some tables to it, and I can do some things to it. There's an endless amount of stuff you can do with it in this software. The software actually has its own programming language within it, so that if it doesn't have the functions built in, you can program it and make it do what you want. So it really is having endless possibilities of what you want to do. But before I continue on to an introduction to spatial analysis, which is the second part, so it's moving beyond GIS into spatial analysis, does anyone have any questions from this morning or from yesterday that are still outstanding? Definitions, things like that. Is there anything that, do we not know what we want to ask? Is that where we're at? Okay, I hope I haven't lost people that much then, and that you're just like, okay, some people, we're doing okay. The lab.
I'm having trouble putting a picture in my mind of what I actually am doing with the data.
Okay.
What's a program thing and what I'm populating Excel and what I'm showing. And
right. So in terms of actually how the data is structured, in terms of what's a layer, what's a table, these sort of things. How do they interrelate? I'll just try my best to go to sort of show you some of that stuff. I'm actually going to load up the actual ARC catalog to do this. So this is the actual, or this is the ARC catalog viewer, not the one within ArcMap. And so here's our various data, our structure with NB data, all these different things. Underneath this SG folder, and same as under the NRCan folder, we have these layers. The icon on this one, it's hard to see right now, but it's actually polygons is what it is what you're showing us. The populated places, you can see it has just 3 dots. That means that it's points. It's telling you what type of thing it is. Each one of these things is a layer, is a spatial data file. What this contains is the spatial data. So that is this listing of polygons, and it contains the coordinate values of each one of these polygons. What are the lines? What are the boundary outlines of it? And that's what it contains. It doesn't contain that's sort of the basic layer of it. So if we were to look at it, these are the files we're talking about. The .shp file and the .shx file. SHP file contains all the shape information. So it contains these actual shapes. You see it's quite a big file. It's like 68 megabytes in size, because there's a lot of information associated with it. There's a lot of polygons. These are census divisions for all of Canada. There's a lot of information associated with it. There's also this DBF file, which a lot of you are aware of anyways. A lot of software reads DBFs. That's a file that is part of the shapefile package, and all it contains is it just contains this data here, which is just tabular data. So each one of these has a unique identifier. Each unique identifier, this FID, it's an internal identifier to ArcGIS. or to the shape file, and it contains a shape that's a polygon. This links back to that .shp file. And then all of these fields here we can open up in Excel. So this field we can't view in Excel, right? It's a polygon. It's the SHP portion of it. So it's not part of the DBF, but it's that associated attribute to that polygon. So this is sort of how it's structured. And these combined together form a spatial data layer. So if I was to add those into here, let's just close these up. And I was to add my census divisions in here. These are my census divisions. I can now map them, and I can view the attribute table in exactly the same way. And I can do things like, just to show you, these are the census divisions in New Brunswick. I can open my attribute table and view only those that are selected. So now I can see I've got this corresponding between these polygons that are in between here. And I can even go through and select just the ones that I'm going through. So what the software is doing is it's visually displaying that .shp, that polygon, and it is looking up on that DBF file the corresponding record. So you can think of the DBF the same as in Excel. It's just going through and finding that corresponding row in Excel that has the data associated with Madawaska. So that's sort of the structure of how it works.
So how it gets to that, is it all the XY around?
It is.
Around the circumference
Yeah.
of the whole thing?
Yep. Yep. It's exactly what it is. Is it actually has the SHP has a listing of they're called vertexes, so vertices, and each vertex has an XY coordinate point, and something like this would have thousands of vertices all around it, depending upon what level it was created at, right? A square could have you could have a square with 4 vertices, right? And that's our square. And it would have, the SHP file would have XY, 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 and it would tell you this is one, so you would have what you would have as a corresponding table, which would have the FID, or the, it's actually just the vertex ID, the X and the Y, and you would have those listed down here. So, and it would tell you these different values. And then if we wanted to make this a different shape, if we added a point here, then you would have it like this, right? And this listing is always in order. It's always listed in order of, if this is point 1, 2, 3, 4, 5, right? If we're to add another point in the middle here, this becomes 5 and this becomes 6. It's always renumbered. So it always gives you a from and a to.
So if we had our own data set that we want to build a layer of,
Yep.
what do we need? We just need to know what the CSD identifier is in order to link it?
Yep.
That's all we need.
So there's a couple different things that you would either need to know. One thing, if you have your own data set, a lot of these things already exist. The census subdivisions, census tracts, census metropolitan areas, dissemination areas, all these sort of things already exist. In that case, you would just need to have in your data that in there. You could have city name, right? That corresponds to CD name or something like CSD name. Other thing you can have is you can have X and Y. So if you have the latitude, longitude coordinate of something, I'm just going to double check and see, does this one have, this doesn't have our XY coordinate points. We can, I don't have an example I can give you, but I can go add data, I can add XY data. So if I have a table that has a latitude and longitude coordinate, and I've got the XY coordinates, so as it's an event, something that happened, an accident, the coordinate point of a hospital, I can just add that data, and it'll show up as a point on there. So that's sort of how we can then relate our data into that. So when we add our data to our map display, here I have this export output, right? I have this census divisions. They're all in there. They're all census subdivision boundaries. They're all just virtual copies of exactly the same file, right? It's one spatial data file that I've just dragged and copied over to here, and I can have 30 different copies of exactly the same thing. So they can all be sitting in there, and we can have them all, one showing population change, one showing median age, but they're all exactly the same file that it's referencing. In the map display, we can just take that file and view it multiple different ways. So
each time you want to show more than one thing, you have to copy it as many times for as many things as you
Yep.
want to show.
Yep, so I could take this population change file that I have here, and I could go copy, paste, bring it down, and I want this one to be median age. I don't like that color scheme. And here, right? I didn't actually create a new copy of this file, right? There's not an actual new physical file on my disk. It's just a new representation of that same file in two different ways. So if I looked at my Windows Explorer here, I still only have one copy of my CSD file. I don't have any more copies of my CSD file. I've just done it. So if I go here and I go Properties, Source, it tells me that it's a shape file, and that's the shape file name that it's referencing. So that layer is that shape file, and I'm just viewing it in this way. So that's sort of some basic structure of what a layer is and what the attribute tables are. I thought that's one of the things that people were going to get. It's just a concept, different terminology and different concepts. So I have that terminology in the presentation that I gave, and I rapidly threw at you guys in a matter of minutes because it was supposed to go leisurely through it and, go back to ArcMap and show you how to do things as I was doing the presentation, but I couldn't because I only had an hour to do it. We had to cut out 4 hours of the lecture yesterday, and as a result, half the slides. Unfortunately, we weren't able to do that. But it is also in the lab. I have some of those terminology defined. And the help menu on ArcGIS is really good. It's actually really, really good. So if we go to the ArcGIS help, one of the things they have is they have this essentials. So what is GIS? Right? How maps contain contain geographic information. They've got an incredible amount of, how maps are used in GIS, an incredible amount of background information on how things are done. So elements of a geographic information system. So if you want to look at the help, it's really an introductory GIS textbook and an advanced GIS textbook all rolled into one. So they've done an incredible job of doing this. You don't really need to go out and purchase one of those $1,000 books on how to use GIS. You can just look at the help menu and it has that. And it also has some of these, the advanced stuff that we were doing. So I just wanted to show you geoprocessing. I wanted to show you some of the examples that I had. ArcGIS system, getting started. They give you, here we go. So they give you all sorts of different options in here, and it tells you details of how to edit values or how to link files. So, and all these sort of things in great detail with imagery. So utilize the help menu system if you want, or just use that as an introductory textbook as well. Anything else? Or should we talk about spatial analysis? Okay, we're going to talk about spatial analysis. We're going to step back from ArcGIS then, and we're going to talk about spatial analysis and spatial processes, and we're going to talk about exploratory spatial data analysis and some basic spatial statistical techniques. And we're going to go through two types of things in our lab. We're going to look at global and local spatial autocorrelation. You don't need to know what that is yet. I'm going to tell you what that is in a little bit. Clustering. We'll talk about that. And we're going to be using a piece of software called GeoDa to do that. ArcGIS also does this as well. GeoDa is a lot easier and faster, and it's just easier to do in a lab setting. So that's why I'm getting you to do GeoDa. The ArcGIS way of doing it can be kind of difficult. One of my favorite quotes, "Spatial is special," said every geographer. So what's different about spatial analysis from statistical analysis? A lot of you do statistical analysis or have done statistical analysis in the past. As I showed yesterday, and as you've seen from mapping and from looking at some of this data, there are some unique properties that spatial data have that make aspatial methods, that make regular statistical methods that we use, averaging, rates, things like that, make them questionable, can introduce additional errors, can invalidate some of the assumptions of, let's say, a standard linear regression. So if we were looking at a standard regression, a logistic regression, or even calculating a rate, spatial data have unique properties where these become then invalid, or we can gain questions about it. And I'm going to show you some of those examples. One of these examples, 1972, this person was actually a professor of mine at University of Texas, Omar Ghali. They wrote an article published in Science, not a small journal, a very, very big journal, very well-respected journal, called Population Density and Pathology. What are the relations for man? Women hadn't been invented in 1972, so it was just man. Human ecology. They didn't talk. It was talking about man in general. So what they showed in this, very convincingly, was that pathological behavior, so high fertility, heaven knows you want to have lots of children, that's pathological. High mortality, high rates of public assistance, juvenile delinquencies, and mental hospital admissions. We know these are all pathological behavior, has nothing to do with social determinants or anything like that. But anyways, they showed very convincingly that these were related to population density. The more people you get living in an area, the more you get these. And they related this, being human ecologists, to like rats in a cage, right? The more rats you get in a cage, the more pathological behavior. So they start to nip at each other, they start to bite each other's tails off. And this was essentially their theory. And they showed very convincingly that when you look at the pathology controlling for components of population density, we had a very large proportion of these social pathologies which could be explained by population density. So a lot of these problems we get in Chicago, in these inner cities, were just because these men, apparently, women weren't there, but were living, it was too dense, these housing things. And I mean, we make fun of it now, but maybe in 30 years they'll be making fun of what we've done. I don't know. Now when we think of that, we're like, that's something about that just doesn't make sense, right? It doesn't jive well. Well, in 1982, finally women were invented, and Sally Ward was the primary analysis who did this, and thankfully so, because she showed that it was actually false. They began to question this idea of population density actually causing these social pathologies. And they looked at just one thing. They looked at fertility. And one of the things they said is that what they failed to recognize is that things like density are spatial autocorrelated. What does that mean? It means that areas where you have highly dense areas are right next to other areas that are dense. So you get a dense neighborhood, it's right next to another dense neighborhood, and to another dense neighborhood, to another dense neighborhood. And the boundaries between these are artificial boundaries. One side of the street and the other side of the street. On the ground, there's no difference between them, right? It's a continuous surface. We've drawn these boundaries and we've assigned values to these, so that your value here of density is going to be related to your value here. There's a relationship that exists between density that exists in space. When we're doing an analysis, such as a regression, we assume that the values are independent of each other, right? We have to assume an independence in the values. We know spatially these values are not independent of one another, that they're related. They're autocorrelated and they're spatially autocorrelated. Well, if we look at the distribution over all of the Chicago greater area, they may be not related, but if we look at them on a map, they are correlated. So it's called spatial autocorrelation. So the effects of density on fertility change when spatial processes are included. And they essentially showed, so this is looking at the rooms per housing unit, that the log of that it was essentially spatial autocorrelation, and that when they redid the analysis done by Omer Ghali and all effects of density were completely wiped out. It had nothing to do with, density had nothing to do with it. It was what you would think. It was income, ethnicity, class. So it was the common things that we would think of. It's a really good example because it raises a lot of key issues. And this is the type of analysis we do a lot in population health, especially, but we also do it in social analysis, and we do it in other things. We're using data that has a spatial component to it that exists in space. And there may be some relationship over and above the tabular relationship that occurs something else in space. So we really need to have some sort of understanding about the elements of spatial data analysis and the understanding of the spatial component of our data, how it exists in space, before we begin to analyze it, because that may be part of it. Now, it may be something just inherent in the data, so density, well, it's just density, right? But we need to take it into account in our analysis, or we just don't include that variable in our analysis because it's not relevant. So we need to be able to look at some of these issues, and I list what these are called here: spatial autocorrelation, scale dependency, modifiable aerial unit problem, people call it MAUP, It's a very common thing, and something called heteroscedasticity. I'm going to give you examples of all of those, because right now they mean absolutely nothing to you unless you teach intro stats on a regular basis. Those are terms you don't use on a daily basis. So why is this important? Tobler's first law of geography. There isn't a second or a third law. There's just one law. And it's called the first law of geography. Everything is related to everything else, but near things are more related than distant things. It's a first law of geography, and it's this idea of spatial autocorrelation, where you get things that are related to each other. And if you think of it in terms of social determinants and neighborhood level analysis, this is especially important, right? It's more likely that other houses in my neighborhood would have similar house price values, will have similar incomes than those on the other side of the city, right? Neighborhoods, you don't generally have a complete heterogeneous mix of neighborhoods. That's not generally the way it goes. Sometimes it's not true. Sometimes they may stick a low-income housing complex apartment building within a high-income area, and that's not necessarily a bad thing. But then you would get a mix of incomes, right? You've got large houses in this area around the university. Most houses are 3 and 4 bedroom. You're going to get more families than you would in a high-density downtown location where you have mostly condos, right? In the downtown, you got a higher density of students because the housing's cheaper, right? So things are more related to other things because they're closer together. And there's real rational reasons for this, right? Some of these, may have other things. You can think of hospitalization and visits to a physician. Well, people in Fredericton may see specialists more often than people living in rural New Brunswick. The specialists are here, or they're in St. John, or they're in Moncton. They're in the cities, right? They're not in the rural areas. So we know that. It's not a need basis, but we know it's because that's the way service is delivered. So these are sort of things that can have a spatial component to them that may be unintended, and if we don't consider that in our analysis, it could skew our results. This is called scale dependency. Do I have examples of this? Those of you in statistics will understand this, and I'm going to go to these maps here, and this is Calgary. These are census tracts. These are census subdivisions. So these are larger areas within Calgary. If I calculate an average at each census tract level, and I calculate an average at the CSD level, I'm going to get very different results either way. I can't take my averages here and combine them to get the average here. This level at which I calculate values is very dependent, and it will influence my results. So the level at which we calculate these things can be different. The same as when we do spatial analysis, what scale we do analysis at has a large effect on what our outcomes are called. Within, when you're thinking spatially, you get something called heteroscedasticity. Observational areas are generally different sizes. The population in southern Calgary, southern part of Calgary there, population 4,950. This census tract in the middle there, population 10,723. We want to calculate a rate, and we don't standardize it. It's going to show information that could potentially be biased, right? We may have a much higher rate of something down here unless we standardize it to the population or our population of interest. So these are some ideas that we're going to have to do. And when we're used to doing that when we're doing statistical analysis, but when we're doing spatial analysis, we have to do exactly the same thing. We just also have to do it spatially as well as statistically. So I'll say, why can't we just use other methods from linear analysis? There are methods in statistics to deal with heteroscedasticity. There's other ways that we can do, other intervening variables we can look at. We can take logs of things. We can standardize some of the results that can get rid of sort of this. I'm going to show you a few maps on why this is important and why we can't necessarily just take these rates. This was from the this was actually from the first Obama election, so 2004. This is the Republican area states versus Democratic states. But then we look at the actual population weighting. Now we map it based on the population in each one of these states. Well, what looked like a huge Republican area, we can actually see it's a much smaller population in those areas. Look at it by county. Republican red, Democrat blue. This is just the 50-50 cutoff, right, that they have. But let's look at continuous color by percentage. So how we represent this information really, can tell a completely different story. MSNBC might produce this one, and Fox News might produce this one. This is a kind of a really cool map. So this is the difference in support for major parties. This is 2008 compared to 2004. So from the Bush, when Bush won, to when Obama won, we have the difference in support. So here we became more Republican. This is the belt that became more Republican over that time period. And this is a really kind of cool map, and I apologize if I offend anyone with this map. I don't apologize.
Is Alaska frozen, or is Alaska not moved?
It must be frozen. Yeah, they're too cold. They're not in there.
Don't change your mind.
No. I got two maps. 1860 map. Each dot represents 2,000 bales of cotton produced. This is the map of where things became more Republican.
It's also, isn't it, where all of the anti-gay marriage
So
stuff is at?
this is actually, what this is actually, this is actually the Democratic, I should say, sorry. The Democratic belt within there is the areas where you have the black population. So this is the areas where you had the Democratic areas within there, which is the black population sitting within there, remains Democratic, whereas the parts outside of that went Republican. So outside of the traditionally black areas of the South. It was just an interesting way of viewing the data. New York Times did that afterwards. So why is spatial analysis different and spatial data analysis? Where does it sit within GIS? GIS is this broader information system. We looked at some spatial analysis. We just did a little bit of that. We did some joining of tables. We did some querying. We did some spatial data querying and things like that. Spatial data analysis is more of a statistical analysis. Geostatistical analysis, spatial econometrics, spatial regression, using either event or lattice data, which we'll get into a little bit, polygon data, and some geostatistical type of analysis. It's the more data analysis, statistical side of the spatial analysis. And ArcGIS does that, and it all sits within a GIS. So if GIS are a set of tools for collecting, storing spatial data, GIS science and spatial data analysis is what looks at the scientific questions pertaining to geographic data. So now we're looking at the actual science and analysis of it outside of just the input, storage, and analysis and output. So it's moving beyond just mapping. It's taking this information that we have that I may have given you before, some of the census data, moving beyond just having the information, displaying it, and actually adding some value on top of just having the data. So let's look at where is the outcome, how does the outcome change, and the locations under studying. Let's look at clustering of things. Let's look at clustering of disease. Let's looking at autocorrelation, where we can have higher than expected values. Where can we get some subpopulation groups? Let's look at low-income population that has increased levels of certain cancers. We can then add value to just the data that we have and begin to look at from a spatial aspect of it. So where things matter. So I'm going to show you a little bit of exploratory data analysis, and we're going to do some exploratory data analysis using Geoda, and a little bit of visualization of showing patterns, and then explaining some of those patterns in spatial modeling. So where's my maps? Here we go. We already talked about that. So I'm going to talk to you about two things today. One thing is called spatial dependence, and one is called spatial heterogeneity. Conceptually, these are very different processes. Each one is different, modeled by spatial autocorrelation. So we're talking about essentially a spatial clustering type approach, when things are clustered in space. And that was the example I gave before with population density. Density is clustered in space. So if we know that, what can we do about it? Well, when things are spatially dependent, it means that there's a functional relationship between what happens in one point in space and what happens elsewhere. So we have a lack of interdependence among the observations. Observations themselves are dependent. It's generally small scale and localized. So these are things that happen, such as density. It's usually something that we can look at just using the data. It's not something that happens at a broad scale, like one side of New Brunswick versus the other side of New Brunswick. It's something that happens within cities, something a little bit smaller. So this is one example of it, looking at cumulative spatial distribution of the cumulative incidence of TB over different time periods. We can see that the cumulative incidence here, here, and here, that if we were to look at the data just as terms of data, we would see that, okay, so we have some areas that are getting higher. We see some higher incidence in some areas. But when we begin to map the cumulative incidence, we begin to see that some areas, our cumulative incidence remains relatively low, that they're not actually increasing. And those that we're getting more incidence rates cumulatively are those same areas over time. So there's a spatial relationship that exists within this. So we may suggest that indeed we're getting some sort of spatial autocorrelation happening in there. There's a clustering of high incidence of tuberculosis. And similarly, we may have a clustering here of low incidence. So areas that are low. So when we're designing programs for intervention, we would not want to apply the same intervention strategy across this whole area. We would only want to look at one area of Taiwan. Spatial heterogeneity is the other side of this, and this is where it's a large scale, non-localized. So where you get different areas that either are non-heterogeneous. So we have something over here which is most homogeneous to this area over here which is completely heterogeneous, right? Some sort of process. And that here we have obvious clustering and we have an a decreasing clustering. So we might get hot spots here and low spots here, but overall it's becoming more random. So this is a really good way of showing of how you can get a heterogeneous form, even though the values here, the number of dark spots, high values, the number of low values, are exactly the same in this one as they are in this one. It's just the spatial distribution of those values has changed. So if we look at it in terms of a tabular basis and linear regression methods, we would get exactly the same results for analyzing this as from analyzing this. Even though spatially we can see that these results are correlated with each other. one of the ways that they've shown this a good illustration, I don't actually have one of those slides here, is looking at spatial segregation in the States, where they look at black-white segregation. It's always black, white, and Latino in the States. And they look at segregation of these different groups. And you can really see that you get this segregation patterns, areas of high segregation versus areas of low segregation, and that you can get either a heterogeneous form in some cities where you get pockets all over the place, or you get really distinct areas. And it depends on the different cities, and it depends on different countries of different forms. We have that same type of segregation in Canada. It's a little bit different, and it only exists in a few of our cities, mostly with immigrant groups. And there's rational reasons for it. In Canada, it's for different reasons than in the States. In the US, it's a legacy thing of racism, generally with the black-white segregation. Whereas in Canada, it's a change in immigration, right? So we have large influxes of different immigration groups moving to different areas. And in some of our major cities, it's quite simply just a matter of where housing is available. And new groups move in, you move into the new housing in the suburbs. And that's why you get these large suburbs of immigrant groups in Canada. But you do get these same things. You get highly spatially clustered groups. So this is a really good one. How do we model these things? Well, all models are wrong, but some models are useful. There's no formal roadmap of how to do this, but what we can do is we can explore some of our data, and we can look at exploratory spatial data analysis. I'm going to get you guys to go through this in your labs. We can look for patterns of spatial autocorrelation. We can map our different variables. And when you're doing analysis and you're looking at things, this just might mean doing what we were doing today. We take our census data and we take our event data and we put them into GIS and we map each one of these things. We map all our independent variables and we look at where they are in space. Are they related to each other in space? How do they look? What if we do our rate by total population? What if we do our rate by the population by employed women? Look at that. And there are a lot of things like that. So what if we look at these different factors and just exploring and looking at patterns in our data. So the goal of exploratory spatial data analysis is just to test and describe and explore, look for clues in this, and then use to inform our choice of linear models. By looking at that, we might say, well, some of these variables don't really make sense, right? If we look at two variables, they may have exactly the same spatial pattern. Why would we want to include both those variables? One, like education and income. Why would we include median family income and the highest level of education in the household? They're pretty highly correlated. Most of us know that anyways when we're doing research. But if we look at them spatially, they're going to be pretty close. So it allows us to look at some of this data. And we can use a variety of different things for that. We can use maps, we can use the descriptive statistics, and different plots and graphics. The clustering and classification methods that you were doing earlier, whether or not you choose the standard deviation, or you choose natural breaks, or you define intervals within your data. And we make use of the dynamic linking. So where we select one area and it highlights it on the map. We look at the table, the value, and we look at these different outliers. Some of you started to look at that with population change. What were these areas that had really, really high population increases or really dropped in population? Why was that? You can click on it and then you can see it in the table. So we can look at some of these things. We can look at some of these different values, and we can see this is the US South. So this is the percent of families in poverty. This is a value called family resource deprivation. They're highly related to income inequality. and they are approximately related to the inverse of the median family income, the log of the median family income. So when we look at it, we can see, okay, so here we have poverty, maximum 0, minimum that, maximum that. We've got a really high standard deviation. Here's the mean. Some of our basic statistics that statisticians look at, right? You know, the min-max deviation means. Some of you may also look at that in your data when you're looking at different, especially in health data, we often look at that. We can then map some of this data. Let's plot it. Let's look at some of these outliers that sit there. Let's look at what are some of these really high poverty areas. We have very few of them. Most sit in here. Let's do a box plot of those and look at each one of those events and see the values and where they sit. Let's look at different poverty versus family income and see how those relate. We can then look at and we can grab some of these outliers and see how these go. And the software Geoda, it has an ability, and I'll show it to you later, where if you select, and ArcGIS does this too, if you select 3 of those points, it will select them here, 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 and in the map. And so you can visually see all these different areas, and you can see these outliers. You can really begin to explore your data. Here's what I show you that. You can barely see it in here. I've selected these yellow areas here. These are the outliers I've selected. So here we are looking at the, I forget what variable I'm looking at. I believe it's the resource deprivation variable, I think. But it's looking at my outliers, those that sit really, really high. You can barely see them here, yellow on the map. It shows me here, here, and a little bit here down by the border. And here's the areas here is where they sit, here in my histogram. So we can then begin to explore our data as to what, we can say, okay, well, those are actually, there appear to be some clustering of that. Why is there clustering of that in those particular areas? So how do we account for that? If we know that some of these variables are clustered in space, how do we begin to adjust for those in our models? I'm just going to grab a drink, sorry. All I'm doing is talking at you. If we assume that values in one area are more related to values in an area beside us, one thing that we might want to account for is say, okay, well, let's adjust our models so that we take into account what the values are of each neighbor. So what are the values of the areas beside us? So if the income of my neighborhood is related to the income of the neighborhood beside me, then let's adjust for the income of the neighborhood beside me, right? So that if I have an area that's very low income, it'll be adjusted differently than areas that have a very high income. So you get a clustering of higher income areas versus areas that are more heterogeneous. The big example that people use is house prices. House prices are obviously very related to census tract boundaries. University Avenue is a census tract boundary. Houses on one side, the house value on one side of the house is going to influence the house value on the other side of the street, right? That's an obvious thing. So if we're looking at house prices and trying to figure out what influences house prices, well, we'd want to know what the average house price in that other census tract is if we're going to calculate it in this census tract as well. And the same thing to do with factors related to poverty. And the way we do that is by using these sort of things, these spatial neighborhood and neighborhood, a matrix of proximities, whether or not things are beside each other, they're contiguous, and we can create a weighting mechanism. And I'm just going to go, I'll show you how to do this. At a very basic level, you have what's called a neighbor. This cell, I'm just doing them as squares here because it's easier to visualize, These can be polygons as well, because each one of those polygons, right, has neighbors that are associated with it. They're just really hard to draw on a screen. It's easier to draw it when you have it as a matrix, as a basic lattice. This one has a neighbor, that's this one. So Tobler's first law of geography, more likely that everything is related to everything else, but near things are more related than far things. So when we're accounting for some of these things, we would be more interested in accounting for this one than we would for this one. However, we recognize that we may need to account for more of them, so we might take those that have the largest boundary. So here we have what's called Rook. They share a common line that's associated with it. Or we have queen contiguity, where we move like a queen does in chess, and it takes all areas that touch a vertices here. So even if it only touches a vertice, it is right beside it. And we can take those into account. So we could also only take those that are, don't share a boundary but are close. But that's not very common. We wouldn't necessarily want to do. So we can then use this to recalculate our rates and recalculate our statistics. And the software does this for us. And it's a really easy way of doing it. Where if these are all values of 1, these are all, whatever, just to show you this is a rate of 1. If I am, weighting it, I could just use the, standard weights matrix to do it. I'm not going to get into this. There's a better way of doing it here. So if this has a value of 5, 6, 3, 4, 4 here, I can weight each one of these by simply a mean of the neighbors. So that would be called a spatial lag, which just gives me a simple mean of the neighborhood values. Or I can give it a spatial weight. I should have put, oh, did I not? I hid some slides here. And I think I hid the one I wanted to, or is it? Oh no, I do it later on. Or I actually provide a weight and I can adjust the values based on, so if I had a value here, I can actually standardize that value based on the values of all neighboring values.
So,
that slide should have been before.
So I understand you get the mean of the neighbors. But
Yeah.
Is it important to look at the difference between this mean and the value of the neighborhood you're looking at?
Yeah, you could do it based on the overall value as well. So you can do it multiple levels. Mm-hmm. So you can do a multi-level weighting. So
Where do you come up with the fudge factors, right? If you take University Avenue, that's obvious that there's a relation. But it's not so obvious with the river because there's only 2 bridges. So
well, they're not adjacent. So depending on what file you use. So the spatial files that we have a set of spatial files that include things like rivers, where rivers are in there, and there's essentially a space in between them. So there's one file that doesn't include these sort of things. So if we were to count, well, you say your fudge factor, for New Brunswick and Nova Scotia, we would be accounting for values in PEI. But because those in that file, the census subdivisions and the census districts are adjacent to each other, even though it's across the water. And we know it's not a small distance, right? My house values in New Brunswick aren't related to the house values in PEI. And same as they don't include, the Bay of Fundy's not in there. It's excluded. And same as across the rivers. So you would not include areas on adjacent sides of the river. There's also other ways of doing it. You can do it either based on just an actual adjacency. So this is adjacent, or you can do it based on what's called a distance weighting. How far away is it, right? So those across, and this is where you said that far things may be related to other far things. We might say, okay, we want everything to be related to everything else, but we're going to have it, those things closest have the highest relationship and those things farthest have farther. So we might say, the ones on the other side of Fredericton are going to have just a small influence, whether they're across the river or not, and those closest to us will have a larger influence.
But in urban, as you know, in urban patterns, there's actually data that are the opposite of converse law, right? Where there's negative correlation.
Mm-hmm.
You have very rich neighborhood completely adjacent to very poor neighborhood.
Mm-hmm.
Saint-Henri, Westmount in Montreal, these two are
Yep.
actually one beside each other. Of course, there's a cliff, so one is actually higher.
Yeah.
But if you look at it from the top, they're adjacent. And we know a lot of cities where these things are. So
Mhm.
How do you account for that?
Well, there's a lot of different theories, and this is where you have to go back to put on your sociological theory hat. And sometimes you might say, okay, well, let's say what we're interested in is we're accessing social services for individuals and access to social services. Well, sometimes we say, well, in rich neighborhoods, there are more things available, right? There are more social services that might be available, or people might be able to have better access to them, nicer pools and things like that. If you've got a rich area next to a poor area, you may have more of these things. It may improve access. There may be a better grocery store that's there, right? It'll allow people to have a greater choice of shopping and healthy foods. Maybe. Right. Some of these things have been shown to have relationships with the average income of the area.
But I think
So.
the limitation is that all these boundaries are kind of on the map. They're kind of a bit arbitrary, and
They are.
Because sometimes a poor person may decide to go shop for grocery much further because they will never go to the fancy store that is closer in the richer.
And that's part of,
because it's a cultural issue. It doesn't want to be seen there.
And that's part of also almost makes it more important why we would want to include adjacency in there. Because we'd say that, well, it is related to everything else around it. That, the access in one or availability, the type of people, the income in one area is more related to the areas surrounding it, not just its immediate neighbors. And in the local level, you get some processes which work. House prices are obviously one of the big examples there are. Access to care is one of the other ones. In rural areas, access to doctors. But on a national level, you get it can actually change the actual relationship of things. One of the examples that I don't have in here is we were looking at air pollution, and we were looking at a Canadian level. We had particulate matter for all of Canada. And we're looking at the relationship to mortality. So looking at the mortality relationship of exposure, long-term exposure to air pollution. The highest polluted areas in Canada are in southern Ontario. We know that, right? Highest particulate matter is in southern Ontario. Concentration of industry, concentration of autos, concentration of individuals. There's some particulate matter flow from the United States that comes over from Chicago and Detroit and comes across southern Ontario. So when we look at it, we're like, okay, so this is where the highest pollution is. Very low pollution in the rest of Canada. New Brunswick's very low particulate matter pollution, not vehicle exhaust or anything like that. Same as in northern Canada. However, southern Ontario also has the highest incomes, the highest education, the lowest poverty on an aggregate level. If you compare the values in southern Ontario to northern Ontario, to New Brunswick, to PEI, it's got higher incomes, higher education, better access to health, higher proportion of immigrants. All these values are different. So when we were doing our initial analysis, we had an inverse relationship with mortality and pollution. So being poor was protective, right? So having lower education was protective because the average education in areas of Canada that had very low pollution was so much lower than in those areas that had high pollution. The average education, right? And this is what you get, this large-scale spatial process occurring. That when we first looked at the data, first cut, we had an inverse relationship. And it was like, what is going on? It took us a while to figure out. And so what we ended up having to do is we ended up having to do a stratified analysis where we took a portion of southern Ontario and we stratified it and we did a multi-level spatial model. So we looked at that and we analyzed mortality relationship there versus northern Ontario versus Maritimes versus southern Quebec, northern. We analyzed all these things separately and combined them then into the model. So we did a stratified analysis, and lo and behold, you come up with the results that one would expect, right? Where you get areas that have lower income and education is in fact protective of mortality from air pollution. But it was simply this large-scale spatial process that was driving this. And we're having that. You also have that problem in a local level with air pollution. And we found this when we were looking at Ottawa. And there's a Kai-Hai report that has this. When we were looking at vehicle exhaust, so NO2. So we have very detailed maps of NO2 for Canadian cities. Ottawa has a weird case, and so does Toronto, where you have some very wealthy areas that are right beside the major roadways. So right beside the Queensway in Ottawa, right beside the 401 in Toronto, you have some very wealthy areas. And so when you look at the relationships with exposure to NO2 and mortality, well, you've got some very wealthy areas where you have higher life expectancy, lower mortality, higher education. They're right beside the areas with highest NO2, highest vehicle exhaust, right? So it's skewing these. We get these outliers that sit right beside these areas, and it ends up making your results really weird when you look at it at a whole level. So we had to do a small local level and assume that we had local spatial autocorrelation. And that once we took into account these local these spatially correlated effects, we would then get the model that we would get then the expected results. And it was because of these outliers sitting there in there. So sometimes these values can come up with something weird. And I mean, we weren't really going to want to publish something that shows that, well, the lower education you have, the less money you have, the longer you're going to live. This wasn't, public health would be like, what? I don't think they'd be really into that. The whole social determinants would be thrown on its head. So these are the sort of things that we're talking about. On the one hand, we're talking about local level spatial effects. On the other one, we're talking about large scale spatial processes. Is that a better explanation of what I was doing? Probably more clear than this. Okay, I've got some nods going, okay, that makes sense. So our null hypothesis is that I really just talked about all of this stuff. I'm going to go through because we've only got like 5 minutes. Because I really did just talk about, we assume random autocorrelation. So here's a really good. So spatial autocorrelation, we posit that like values tend to cluster in space. Normally, in a linear model, we would assume a null hypothesis that all values are spatially random, right? So in a regular statistical analysis, we assume that there's some sort of randomness, that values observed at one location don't depend on the values observed at another location. So we assume some sort of randomness. So alternatively, in the spatial approach, we assume that they tend to cluster in space. So this is the actual map of the US with the percent of the black population by county. This is if we randomized it. So as a statistician, there are 3,085 counties. This would be very unlikely given the 3,085 possible permutations of the percent of black population that you would end up with, that this would be random. So this is clearly not a random thing. And it's obviously, we know why it's not. There's multiple historic reasons for it. So this is what we would call global spatial autocorrelation. So there's two levels, global and local. Do the data as a whole exhibit a spatial pattern? So this is what I was talking about with the air pollution at a national level, or are there local indicators of spatial autocorrelation? Are there specific areas that have that are more related to other areas within a local level? And we can look at these sort of things. So globally, we can look at, okay, we have things that are obviously have clear spatial autocorrelation at the global level. We have the percent of African American within the US that, you know, there's clear global autocorrelation. We know that we have some counts in here. I'm just gonna gloss through these. And if we do something what's called a global Moran's I, which is a statistical test for whether or not this autocorrelation exists, it approximately varies between 0 and 1. Higher value means that there's more autocorrelation. We can see that, yes, indeed, you know, we've got this really clear pattern. We do have global autocorrelation of these values, percent black. We didn't need statistics to tell us that. We all know that implicitly. Not all things we know that for. There's another example of that I'm going to say. We can also calculate this at the local level, so not a local spatial autocorrelation. And this is where we account for the values within each neighboring area. So in this case, we have all 6 values. So let's look at an example of the log of the median family income. Income we often take the log of. And we can see higher incomes in certain areas. And we see that, yes, there's potential for spatial autocorrelation. We look at our global Moran's I, that it's 0.677. We do have some global autocorrelation. Things are related globally. And when we map it, we can say that at a local level, we do indeed have some areas where we do have some significant correlation. The areas in darker green are more significant. So not only within the national level are they located, is there some correlation, but these areas here have even more clustering of it. And we can then map those. So we can say that these areas here have higher than expected values of high income, and these areas here have lower than expected values of low income. So we have clustering of high and clustering of low. And these are significant to 0.001. We can then do that in the test. So we can then do a statistical test and say, okay, this is where we have significant differences. We can also do the same thing for rates of health. I may have hid that or taken it out completely. I don't have that in here. One example that I also have is I also use that. There's an example, and we're actually going to do it, I think, in our lab. SIDS deaths, in that when we look at the actual rates of SIDS deaths in some areas of the States. There's another Scottish lip cancer study, they also show that. You end up with the same thing. You end up with areas that have higher than expected high rates. Even given, you can even use multiple variables including it, even given other variables included in terms of age and racial composition, ethnic composition, things like that. Racial composition, they always talk about in the States. They don't have ethnicity, they have race. But you can also include it in terms of health outcomes, or we can include it in terms of social outcomes, determinants of poverty and things like that. So one thing to keep in mind with these is that these measures that we're going to be talking about today are scale dependent. The Moran's I for something like this is 1.0. These are not adjacent. These are not adjacent. We have a perfectly clustered area. This is a value of 0.33. These values are adjacent to each other, these ones and these ones. So you end up with a much different measure of spatial correlation simply because we have different scale dependency. This is just something to keep in mind. So what we're going to do after lunch, and it's exactly noon, now that I've ran through that, yeah, I've been like literally running through this, like I've been jogging. We're going to actually do some of the stuff that I've just thrown at you, and we're going to map some of these things. It's really, these ones are really like, do this, do this, do this, do this. Okay?
Thanks, Paul.